All right. Okay, and so yeah, here we are going to cover Newton's three laws now. First and foremost, you have Newton's first law of motion, which just briefly states that an object in its state of rest or uniform motion will remain at rest or uniform motion unless a resultant force acts on it. So this is something that you've already learned in Sec 4, and it implies two things. Firstly, for an object to continue in its state of rest or in uniform motion, that means constant velocity in the same direction, then there is no required, there's no resultant force to maintain. So I always give my students this example. If you were in outer space now, and you are very far from any object, any planet, in other words, the gravitational field is negligible. If you were to throw a tennis ball into space, and you throw it at 5 meters per second, it will continue, right, at 5 meters per second indefinitely. In other words, you do not need a resultant force to keep it going at that speed. So that is one of the implications of Newton's first law. The second thing is that the state of uniform velocity requires no resultant force as well. So these are two things that you need to know. And likewise, you can also say the opposite, which is in order for you to change the motion of an object, then you require a net force. So quite a basic concept. Now, this is linked very closely to inertia. So inertia of an object or a body is actually the measure of its resistance to change motion. Okay, so this doesn't mean that, okay, or rather, I'll say it this way. The resistance to change motion doesn't mean changing velocity from something that's very fast to stopping the body. It could be the opposite, right? You also resist the change of motion from rest to now going to a higher speed or higher velocity. And so that is exactly what I mean when we say resisting a change in motion. Now, as you all already learned from Sec 4, the degree of inertia depends very heavily on how massive the object is. Generally speaking, any massive object will definitely have a higher inertia than one that is less massive. So a very, very common example, right, that you always see in textbooks is like an elephant versus a mouse. An elephant is very agile. It's able to change its direction. An elephant is it's not agile, right? Your mouse is agile because your mouse is very small and it's very low mass. But for your elephant, if it's running and it wants to change direction, it requires a tremendous resultant force. And so that is the measure of inertia here. And this is just something that you might be tested on in your promos. Now let's move over to the second section. Okay, and this is where Newton's third law comes into play. So I want you guys to remember Newton's law in terms of two different bodies acting on one another. So it goes formally in this way. If a body A exerts a force on body B, then body B exerts an equal but opposite force on body A. Now, I want to clearly define, right? Actually, there are three inherent properties here. So to make this a bit more precise, I'll write that for the forces here, okay, the forces are of the same type. Okay, and so this implies three things for an action-reaction pair. Okay, so I'll just write out on the side here. Three conditions for AR pair. Okay, so here are the three conditions. First and foremost, you need the two forces to be equal in magnitude, but opposite direction. Okay, that's the first one. Second thing that you need is you need both of them to have the same nature. So this is what we've covered just now. When I talk about nature, I'm referring to the type of force, meaning a gravitational force, a magnetic force, an electric force, or a contact force. They have to be the same kind of force. Okay, so it's a very, very important rule here. And so if you're very mathematically inclined and you want to put this into an equation, then this is what the equation looks like, where force of A on B is equal to the negative of force of B on A. Now, why is there a negative sign? The negative sign just indicates the direction. So given that A exerts a force on B, B will exert opposite direction force on A. Therefore, you have the negative sign there. And the magnitude is identical to one another. Okay, so this actually ties in line out very, very nicely with one of the more important concepts in JC1, which is the conservation of momentum. So later we'll be doing a question, and I hope that you find the beauty in physics when I cover that question. Okay, but for now, let's move on first. I want to cover some more content before we start on the questions. So here's one simple example. If you have exerted a force on, let's say, a desk, right? Then the force that you exert on the desk is in this direction. You just naturally experience opposite direction of force on your hand of the same magnitude and of the same kind, meaning both of them are actually contact forces and have the same magnitude, opposite direction. So these are action-reaction pairs. Okay, moving over, same thing here, right? You have this lady who is pushing herself off of the swimming pool, right? You can see that the idea here is, once again, these two forces are action-reaction pair. They fulfill all three criterion, and thus it's clear the action-reaction pair. Now, I'm going to bring in a very important concept which I've taught, well, my students, okay, and some of you in Sec 4 might have had this massive misconception. So look over here, okay. If you consider the lady here, right, she's experiencing a weight down and a normal contact force up. Now, one of the biggest misconceptions are in Sec 4 is you thought that these were action-reaction pairs. But now let me debunk that. Remember, there are three criterion, right, for you to consider two forces as action-reaction pair. The three criteria here are not met. Okay, I will draw out a little diagram for you. Give me a sec, I'll add in a page. Okay, awesome. So let's say this is the person in consideration, and this is the weight, right? And this is the normal contact force. Okay, so they're supposed to be acting on the same line, but I just want to draw it separately so that y'all can see it a little clearer. These two are not action-reaction pairs. First and foremost, right, let's recap what are the three criteria. Right, first one is equal magnitude, opposite direction. So this one is fulfilled. It is fulfilled. The weight and the normal contact force for the lady or the man there in equilibrium is the same. Correct? So that's why there's no net force. But you see, right, the other two conditions for this case crumble. Why? Are they of the same nature? The answer is no, right? You know, one of them is a contact force, the other one is a gravitational force. They are not the same. So you know that these two are straight away, right? Because they fail criteria number 2, they are not action-reaction pair. Okay, then look at the last one. They must act on two different bodies. Right? So in other words, remember just now in our definition of Newton's third law, right? It's A acting on B and B acting on A. Do you realize that both of these forces here are acting on the same person? Therefore, 3 is also not fulfilled. So you know that NCF and weight are just not action-reaction pairs. Okay, so here's a mind-blowing thing, right? Every time I explain this to my Sec 4 students, I think they are very they're very impressed and they are very astonished about physics. So what would this action-reaction pair of weight be? If you have considered this, right, you know it needs to be the same nature, correct? So all of you guys now, right, have you ever considered what is your action-reaction pair of your weight? Because you know that the Earth is pulling you down now, and you know by Newton's third law, there must be an action-reaction pair. But what is this action-reaction pair? Okay, so here's the fascinating part. Think about it this way. This is Earth. You know that Earth is pulling you down. In other words, Earth is exerting the gravitational force on you. So actually, the action-reaction pair is the gravitational force that you exert on the Earth, which is upwards. Okay, and I guess this one is not so surprising when you've already learned gravitation, right? Where you learn that, right, G m1 m2 over r squared, that's your gravitational force that you experience as well as that you exert on the Earth. These two are equal in magnitude and opposite in direction, right? They also act on two different bodies, one of which is the person, one of which is the Earth, right? And so that's why these are the two action-reaction pairs. So, okay, you can see here. These are the two pairs of action-reaction. First one, gravitational force that the Earth exerts on the lady, which we often call as her weight. And the second one is the gravitational force that the lady then exerts on the Earth. So this is the first action-reaction pair. Now, you also know that, well, if there's normal contact force, there must be an action-reaction pair to that as well. So the other pair will be the normal contact force that the lady exerts on the floor, and subsequently, the normal contact force that the floor exerts on the lady. So these two are the two different action-reaction pairs in consideration. Okay, moving on. Okay, we won't go through this practice example because I think it was a foundation building thing. I want to rush through, or rather I want to go over to the harder 5 prepared questions I've already sent on the chat. Okay, those are the ones I'm spotting for your promos and A-levels. Now, before we go over to momentum, just take a look. Momentum here is defined as rho, right? So you guys use the symbol rho to define momentum. And momentum, right, it's a vector quantity. And it is the product of an object's mass as well as its velocity. So this one shouldn't be new to you. You should completely know this all, especially if you've been paying attention in classes, right, and in your school, right? So you can see that momentum is going to be a vector. And I just want to add in one little pointer here. The change in momentum is also a vector quantity. So meaning if you ever consider, well, final momentum minus initial momentum, this is known as your change in momentum, right? This is a vector. This is also a vector. And so you can obtain the change in vector, in this case, the change in momentum, also as a vector quantity. So, okay, I'm personally predicting this, that it's most likely to come out for your promos if you're doing this. So later that one question, right, that I give to you, I've seen it like plenty of times in a lot of promo papers. And it's supposed to be a giveaway as long as you study. You'll be using cosine law usually to solve this. Okay, so don't worry, I'll take you through that in a short while. Okay, if not, let's move over to Newton's second law. So this is the bulk, right, of what you are tested on. Newton's second law of motion states that the rate of change of momentum is directly proportional to the net force acting on an object. Okay, and the resultant force occurs in the same direction as the change in momentum. Okay, so there are 2 particular statements to this. Do not only think that it's about the rate of change of momentum, the direction matters as well. Okay, don't worry, later when we do the question, you actually get a deeper understanding because you'll be forced to draw out the vectors. And then you can see what I mean when I say they're in the same direction. Okay, if not, you can see basically F net is the same as resultant force. So you can use them interchangeably, they are the same thing. And it is the rate of change of momentum. That's it. Okay, and from there, yeah, you'll have most of your questions tested on this main concept. So this is the one of the biggest jumps, right, from Set 4 to J1, J2. So if you are revising for your dynamics out of your, well, 18 to 20 topics for your A-levels, do make sure you put a bit more time onto this. Every year there will be one dynamics question, guaranteed, like for sure. It's not one of those where the A-levels might not test it. Definitely test it. So spend some time, go and do plenty of practice on this, and then you should be good. Okay, moving over here. Yeah, okay. I think okay, for all my students, right, you've probably seen this like, no exaggeration here, at least your 10th time for your slope-based questions. So slope-based questions are very popular in J1. They love to test you on resolving forces, right? So for resolving of forces, you know that you can always split a vector, right, into 2 directions, 2 perpendicular directions. So in this case, whenever you're given a slope, the key objective is usually to resolve the forces in the direction along the slope. Okay, the reason why you do this is because the normal contact force, right, when you resolve it along the slope, it disappears. And this one should be clear to you. So let me draw it out. You realize that, well, normal contact force, as the name implies, is normal. It's perpendicular to the direction of the slope. So if you resolve along the direction of the slope, you're actually going to completely eliminate it. And so that's why usually you are better off resolving along that direction. Okay, but there's also another intuitive reason as to why you want to resolve along the slope. The intuitive reason is because if you consider, let's say, this box on the slope, right, you know that it can only accelerate along the direction of the slope, right? You won't see that the box, right? The box won't vertically accelerate down. It won't sink into the slope, and the box also won't fly out of the slope. So logically, right, you can more or less predict that if there's any meaningful acceleration you're finding, it should be along the slope, because the slope is where the box moves along, right? If you're pushing it up, it has to go along the trajectory of the slope. If it's sliding down, it has to go along the trajectory of the slope. Therefore, you should always be resolving along the slope. Okay, but there's one caveat here. There's one caveat here. So for most of you guys who have already done circular motion, there's one case, if they ever give you a banked slope, then you don't resolve in the direction of the slope. Okay, so you can write here, except for circular motion with banked slopes. Okay, and so what I'm talking about is, you know, right, on the a lot of circular motion papers, they'll tell you that, oh, one of the ways, right, in order for you to decrease the turning radius of a car is to have banked slopes, because they provide a normal contact force right here with a horizontal component that adds on to the centripetal force, allowing a car, right, to turn horizontally with a smaller radius. So, okay, I won't go too deep into circular motion now because we're a bit tight on time today. So if you're keen, okay, you can go and look into this. I'm very sure most of your tutorial books will have this. So all other cases, usually for forces especially, you want to resolve along the direction of the slope. For circular motion with the center of the circle being here, then you resolve horizontally. Okay, so this one should be quite intuitive also. Let's move over to the next page. Okay, so wait, let's head over here. The next thing that you'll also be given is tension questions. So for tension questions, just come up with two equations, okay, or you can view it as one line, like what I've done usually. So in particular, you know that this tension, right, along the rope is identical on the left and on the right, meaning this tension here is the same as this tension here. Okay, and so you usually will have questions where they ask you to come up with simultaneous equations to solve for this. Okay, yeah, I got a little question. Can I repeat the part about resolving when there's a bank slope? Yeah, okay, so I'll just quickly iterate through that again. So give me a sec. Okay, I got free space here. Okay, so as I was saying, for usual forces question, you want to resolve along the direction of this slope, this direction. So usually, right, they'll give you like a problem where, let's say there's a ball sliding down and you are interested in its acceleration along the slope. Then you'll resolve with this axis in mind. However, there are some questions whereby there's an object, right, that's going around, or rather there's a car that's driving around in a circular bank. So for example, let's say this is a car and the car here, right, is moving around in a circle like this. So let's say like an F1 question, they can ask you, okay, there's a circular turn and this car is going to move around in this direction. Then in this case, you do not want to resolve along the slope. You don't want to resolve in this direction. Okay, the logic is because your centripetal force, also known as your center seeking force, is always going to point towards the center of the circle. Okay, so for those of you who have already done your revision on circular motion, you should know that the centripetal force is a resultant force and it always points to the center of the circle. So for cases whereby you have circular motion and a slope, then the objective wouldn't be to resolve in the yellow line or rather the slope direction. Rather, you want to resolve towards this axis, which is to the center of the circle. Okay, so hope that was clear. If there's enough time later, I'll actually show you what I'm talking about in one of the actual questions, whereby they do give you like the parameters of like velocity, radius, weight, and the normal contact force. Yeah. So hope that was clear. If not, if you are looking over at just normal forces question where there's no circular motion in consideration, then you should resolve along this direction of the slope. Okay, so let's move on. Where were we? I think we were here. Yes. So for your attention in a road questions, usually the objective is just to come up with two equations on mass 1 and mass 2. And for these kind of questions, right, actually what you should know that there are just two catches here. Two very simple catches, meaning if you know these two, it's very easy to solve. Okay. The first one, okay, so I'll write here, two things you must know. Okay, the first one, they have the same acceleration in terms of the magnitude. Okay, in case you're wondering why, okay, why do they have the same magnitude or acceleration? Well, because they are connected along the same string, right? So if let's say you want to think about this in an easier way, right? Imagine if you drag your friend and then you go and run. So you hold your friend's hand and then you just run. Naturally, right, both of you, okay, assuming your hands are already taut, that means they're tight, okay, and your hand cannot stretch, obviously, then you both will have the same motion, right? You both will be moving together, and therefore you have to have the same exact acceleration. In the same way, if you're connecting mass 1 and mass 2 here along a rope which cannot be stretched, they definitely have the same acceleration. Okay, so that's a very simple first thing that you must know to come up with your equation. The next thing that you usually required to do, or that you should know, is that the tension is the same in magnitude. Meaning this T1, right, and T2, they're identical. So if you know these two things, it's actually very simple to come up with two sets of simultaneous equations, and then you can straight away solve for the unknowns. And usually they'll just ask you for one unknown, right? They could ask you, for example, what is the acceleration of the system, or what is the acceleration of mass 1 and mass 2? Then by all means, go for it, right? You should be able to solve it. So this one is quite simple. Okay, but something that they love to test in J1 as well. Yeah, the condition is true regardless of the masses for both of them. Yes. Okay, let me admit some people in. Okay, so yeah, that's tension in consideration of dynamics. Let's move on to the last set here. Okay, perfect. Now, linear momentum and its conservation. Okay, linear momentum and its conservation is actually an extension of Newton's laws. So later I'll be going through this particular set and explaining how it comes about. But one thing that you guys already would know is, well, the principle of conservation of momentum, which just states that the total momentum in an isolated system must always remain constant. So the total initial momentum is exactly equal to the total final momentum, right? And there's one condition: there is no net external forces acting on the object. That's when you know that the momentum is conserved in the system. Okay, and here momentum, once again, it's mv, and the units, right, you can obtain from using your chapter 1 knowledge. The units of momentum is the units of mass multiplied by the units of velocity. So you have kg meter per second. Okay, another important concept that you must now know is you can also find, right, momentum from a force time graph. Okay, so take note. For example, like look at this, right? You have this area under this graph, right, representing as the impulse, which is also the change in momentum. Okay, so from here, right, I hope you can also see that the change in momentum, right, can actually be you can actually find the units of the impulse as force times time. So Newton seconds. So that is actually the unit of impulse, which is also a valid unit for momentum. Okay, and where did this come from? Right, the idea is from Newton's second law, right? Because look over here, resultant force is the rate of change of momentum. So if you integrate both sides, you get the change in momentum. Okay? And so that's the key idea here. So I think quite a basic thing, but something that they love to test. Okay. Now, moving over to the impulse momentum theorem. So as I was mentioning, if you go and find the area under the force time graph, you get the impulse, which is also the change in momentum of an object. Later, we'll be doing a fun question where you consider two balls in a system that exert forces on one another. So when they exert this force on one another, you're actually able to find the change in momentum of each block. And actually, it will prove to you the law of conservation of momentum. Okay, so that is one of our practice examples. Okay, like I mentioned, right, if you haven't already downloaded the worksheet, please do. Okay, these are the questions which I'm really spotting for your promos and your A-levels. Okay, and it's a very fundamental concept that I want you all to know. Okay, the next thing is also considering average versus instantaneous force. So average force, right, is just basically finding, okay, on a graph like this. Okay, let's look over at this graph. If you have momentum and time here, tracked out like that, right? Then if you're ever finding average momentum, you're finding the total change in momentum over a time period. So in this case, my time period that I'm considering for average, so right here. The time period I consider is from T1 to T2. This whole section of time. If I want to find average force, then by Newton's second law, right? Give me a sec. By Newton's second law, the average force, which you indicate with this little cute arrow brackets, okay, is actually going to be the change in momentum on time. Okay, so in other words, you're taking this value, which is the change in momentum from T1 all the way to T2, divide by T2 over T1. So in other words, equals to, right, over T2 minus T1. Okay. On the flip side, if let's say you want to find the instantaneous moment at one exact point in time, then you need to go and straight away differentiate at that point. So you know how to differentiate, right? The most basic methods is to just draw a line, a tangent line, to that point of that graph and find the gradient there. So instantaneous force, on the other hand, will be by N2L, which is also the gradient of graph at T3. That's it. Okay, so if you're given this, then yeah, just be aware of the differences between average force as well as instantaneous force. Okay, if not, yeah, wow, I'm really wanting to quickly get on to the questions. I think that'll be more fun. So yeah, I think, are we done? No, okay, I got one last thing to cover, which is the law of conservation of momentum. So remember, right, the law of conservation of momentum states this, okay, that the total momentum of an isolated system remains constant. Okay, what is isolated? Isolated means there is no net external force on the system. Then you know that it is isolated. Okay, so right, there's this very heartbreaking story. Okay, so one of my J2s, he was studying a lot for his J2 topics. Then after that, he did a revision, like a last minute revision for his J1 topics. So he sort of rushed through the content and he just memorized this formula. I hate that. No, you know why it's bad or not? Because in the exam, right, they can twist and turn the data as well as the content in the question. That it might not be exactly MAUA plus MBUB equals MAVA plus MDVB. So I don't like students memorizing this. It's very confusing. Plus, you already got so many things to memorize over your 6 subjects in JC. Why would you want to memorize this? Do not memorize it. Understand it. In other words, you shouldn't be thinking of this formula only. Your brain, right, when you think of conservation of momentum, right, it shouldn't be writing MAUA plus MBUB equals to MAVA plus MDVB. It shouldn't be that. It should be starting off with the initial total momentum is just equal to the final total momentum, right? Then you consider, before a collision, what are the total momentum of all the things in the system? After the collision, right, then you look over for final momentum. What is all the momentum that you can add up? That's the way I want you to memorize this concept, not a fixed formula, right? Like for example, if you look over at this, okay, MAUA, MBUB, MAVA, MBVB, this works for collision of 2 bodies. And it's very common that you're testing on collision of 2 bodies. But what if like your prelim come up with a 3-body collision? Then how? Then this will crumple already. This won't work already, right? So the overarching formula that you should have in your head is this: initial total momentum of the system is final total momentum of the system. And then, right, you'll be a lot safer for the exams. Okay, so I hope I brought my point across. Don't blindly memorize. You have to understand what's going on. Okay, yeah, if not, yeah, let's move over to Newton's third law. Okay, actually, right, I'm going to skip this because we're doing it together in a practice question. Okay, we're doing it together in a practice question, so relax. We'll push this aside for now. Okay, now we're talking about collisions. So a collision is when two or more objects collide with one another and they exert forces on one another. Generally speaking, you can broadly classify collisions in two forms. Firstly, you have elastic collisions. So an elastic collision, right, is a collision where the kinetic energy is conserved before and after the collision. Now, you have to know that during the collision, kinetic energy is not conserved. It is converted temporarily into usually elastic potential energy or some other form of energy. And then finally, it's then converted back. Right? It's then converted back after the bodies separate into kinetic energy again. So you have to remember this. Okay, during the collision, it is not conserved. It's converted in some other forms temporarily, but as they separate after collisions, then the kinetic energy is conserved. Okay, so this is a very popular promo question or prelim question, right? Where they ask you, oh, mid-collision, is Ke still conserved? You must know it's not necessarily conserved, okay, because it's converted to some other form temporarily. Okay, and for all elastic collisions, you have this particular formula where the relative velocity or the relative speed of approach is equal to the relative speed of separation. Now, the derivation is actually not very challenging. If we have enough time, I'll derive the elastic collision formula for you so that you don't blindly memorize. Okay, on why is it converted mid-collision? Okay, so let me give you an example. So, okay, if you have already covered electric potential energy or electric fields, you consider a collision between, let's say, positive charge Q1 and positive charge Q2. So before they collide, they both have speed U1 and U2, right? And as they go closer, this energy, right, is converted from kinetic energy into electric potential energy. And once they collide, once they go very close to one another, they exert a very large force of electricity or electric force on one another, and then they finally separate. So this is before collision. This is after collision. Right, so the two objects are, let's say, talking about Q1, when they move off, they will have the same final speeds, or rather, they'll have the same total kinetic energy of the whole system after that. Okay, but during mid-collision, actually, they both eventually come to a standstill and then they repel one another. So you have to know, right, mid-collision, the Ke is not actually conserved. Someone who's... Okay, great. Okay, and now, well, if it's a bit too far-fetched for you when I'm talking about electric fields, then perhaps I could give you a simpler example also. So give me a sec, let me draw it out. Okay, so for instance, right, you consider two balls A and B. Before they collide, they have initial speeds U1, U2, and during the collision, right, before they separate with one another, actually they are going to be slightly deformed. Okay? And when I say the word deformed, if you remember from forces, elastic forces, the shape of the two balls actually change such that they are temporarily compressed. And during the compressed section, right, both of them actually gain elastic potential energy. So temporarily, when both of them are squeezing in, right, you're actually changing Ke into elastic potential energy, which implies that the kinetic energy, while they are still colliding one another, right, is not necessarily conserved. It's converted into some other form. And finally, right, once they begin to separate like that, then Ke is converted, your Epe is converted back into Ke. And then the collision is considered elastic. So this is before collision. This is during collision. And this is after collision. Okay, so let me fill it up to be a bit more precise. Okay, so once again, during collision, just note, Ke converted into Epe. And then after the, rather as they are separating, EPE is converted back into KE. And KE final and KE initial are equal. But in the middle, right, during the collision, the kinetic energy has temporarily decreased. Okay, so I hope that was clear. Is it all elastic collision KE not conserved? Yeah, you can generally say that, right? Because there has to be some conversion of energy at some point into some other form, and then as they separate, then it's converted back to KE. Okay, so generally speaking, usually the questions, right, will then be asked only for you to find the speeds after the collision, right? Knowing fairly well that the kinetic energy is conserved overall, right? So usually it will only be tested on that. Okay, so later we'll go through one of the typical questions, and then you can see the style of asking. Okay, if not, moving over. Yeah, one last thing. Sometimes they'll ask you to describe collisions, right, in two ways. So the first thing is explaining what is a head-on collision, and then finally clearly explaining what is an elastic collision. Okay, so as I was saying, elastic collision, right? I'll just cover the second one here first. Okay, it's when your KE of the two bodies is conserved before and after the collision, right? And you know when this occurs, the relative speed of approach is equal to the relative speed of separation. So there's a formula for this. It's also written above. U1 minus U2 is V2 minus V1. Okay, so this is one thing that you must remember. Okay, and well, if it helps you understand a little better, okay, because I don't like to memorize things without understanding why they're called, like for example, relative speed of approach versus relative speed of separation. Right? I hope you all get it in terms of like why they call it the relative speed of approach. So if I were to draw the two balls for you, let's say we're talking about ball A versus ball B, right? Ball A has a speed of UA, and assuming let's say both of them are moving in the same direction, right? Like UB like that. Okay. Then you know that for them to collide, right? For them to collide, UA must be faster than UB so that they catch up, right? So UA catch up with UB. And so if you think about the relative speed of approach, it's just basically how fast A is moving relative to B so that it can catch up. In other words, the relative speed of approach should just be UA minus of UB. That's how much faster A is moving relative to B, and therefore it's called the relative speed of approach. Right? Okay, so hold up. Okay, so this is before collision, right? Before collision, and this is RSA, relative speed of approach. Okay, this is relative speed of approach. Sorry, Summer, what was the question here? Was the relative speed of approach okay, guys? Oh, RSA is just relative speed of approach. In other words, how fast A is moving relative to B so that A can catch up. Right? That's the relative speed of approach. It should be the initial speed of A minus of the initial speed of B. And because it needs to be faster in order to get to catch up and collide. Okay, so after collision, right? You know that B will bounce off of A, right? And you'll move faster than A. So let's call this UB and UA. Right? And in order for them to separate, then you also know that, well, the final velocity, so let me write this as V, final velocity. VB will be bigger than VA, so that B can move ahead of A. Okay? And so actually, the relative speed of separation, logically, should just be how much B is moving faster than A. Right? And so this is how you actually get this formula here. U1 minus U2 equals V2 minus V1. It's just a simple way to say that the relative speed of approach, which is UA minus UB, should be equal to the relative speed of separation, which is now VB minus VA. Okay? And so sometimes your schools will just record this as They'll record this as U1 minus U2 equals to V2 minus V1. Okay, so either way is the same. If you use A or B, it's no problem. Okay, but I hope you all understand this, right? Because in exams, right, it's a bit hard to memorize this, right, without any context. It's just like numbers on the screen. And then it gets very easy to forget. So I hope you all are understanding why they call it speed of approach versus speed of separation, right? Then you don't memorize blindly. Then it's so much easier to attempt physics really. Okay, so yeah, that's my philosophy when I teach physics. I want you to understand deeply so that you don't go in like blindsided, having to memorize a lot of nonsensical equations that don't make sense to you. It should be that you appreciate the equations for what they are trying to explain and you understand the logic behind them. Then it should be very easy. Okay, now let's move on to great. It's time for the practice. Okay, my favorite part of today's lesson. Come, I'll give you all some time. Okay, a tiny break. So a little 2-minute break. For those of y'all who are mentally quite shagged already, you can go and take a tiny breather. Okay, I'll resume at 8:21. I want you guys to get out your worksheet here. So I've already sent this on the chat. If you're ahead, right, you can go and start with this worksheet. And then I'll be solving all of them on the spot for you. Can? Okay, we'll resume at 8:21, but I will cover relative speed of approach again because I'm getting a question here. So give me a sec. Okay, so we know that for elastic collisions, the relative speed of approach is equal to the relative speed of separation. Okay, and your schools might sometimes just write this as U1 minus U2 equals to V2 minus V1. Let me write it a bit sharper. Okay, and so the thing is, a lot of students, right, they try to memorize this and then they don't understand what's going on in their exams, right? They don't write out the correct formula and so they get it wrong. Okay, so what I want to do is actually to get y'all a better understanding of why they call it speed of approach versus speed of separation. Okay, so when we say speed of approach, we're talking about how one object will catch up with another and therefore approach the other object. So if I call this ball 1 and it's going to collide with ball 2, you know that for it to collide, the initial velocity of 1 must be bigger than 2, right? So that it can catch up, close the distance between them, and then finally collide. So if we are considering what is the relative speed of approach, you can think of it as how much faster is object 1 moving than object 2 so that it can catch up. Therefore, the relative speed of approach is U1 take away U2. Can? Great. So I got a very good question from someone asking, what if the balls are traveling in opposite direction? It will still be the exact same working and the same exact formula. So the relative speed of approach will still be U1 minus U2. Right. Okay. And now let's cover why relative speed of separation is V2 minus V1. So think about it this way. The balls have collided already, right? Just assume, right, that ball 1 caught up with ball 2 and they are smashing one another now. Now ball 2 is now starting to move off from ball 1. So the implied logic is if ball 1, right, and ball 2 separate after the collision, then you know for a fact that the final speed of ball 2 must be greater than the final speed of ball 1. Why? So that it can separate lah. So that ball 2 can move away from ball 1, right? For separation to occur, the ball in front, ball 2, must be moving faster than the ball behind, which is ball 1. Therefore, relative speed of separation, you can think of it again as how much faster is ball 2 moving relative to ball 1, right? So it's V2 minus V1. That's the logic. Okay, time's up. So for those of y'all who are taking a mental break, come back. We're going to do the questions now. These are the 5 questions which I feel have a big shot at coming out at your promos or your A levels. So let's have fun with it. First one, okay. A ball is released from rest along a slope. Okay, so you see this, right? You should be very triggered. You should instantly say, okay, I know what they're probably going to test me. And the trick, resolve in direction of the slope. Okay, and they tell you that it's inclined at an angle of theta to the horizontal. So given that the friction is negligible, express initial acceleration in terms of gravitational field strength G. Okay, so actually, right, my VJ kids, okay, so those of y'all who are with me at AMA, this was your CT1, CT2, I don't know. Okay, it came out right. So come, we'll review this again, I'll recap as to why this was the case. So let's draw a little slope first. Okay, draw a little slope, label this as theta. Okay, draw the ball here. Okay, and draw that is well, accelerating from rest. Okay, so now remember, right, you need to consider the system and define it well. So what is the system that we consider? Is it the ball or is it the slope? It's the ball, only the ball. You do not care about the forces acting on the slope, only the ball. Okay, so if I were to draw a free body diagram, I only care about the forces on the ball. So I draw W. Easy peasy, right? Then you also know there's one more force acting on it. That force will be the force exerted by the slope on the ball, which turns out to be the normal contact force. Okay, this is the normal contact force. All right, and now, right, it gets a bit challenging because you're like, wait, what? How do I resolve this? And how do I find the resultant force? So remember, what was the trick? Resolve it along the slope. That's it. You know that the ball, right, will roll down the slope. So you only care about the direction of the slope. Okay. In other words, which axis do you resolve for? Just this axis lah. That's it. Okay. So now let's do a little analysis with the angles here on what this resultant force will turn out to be. So all eyes carefully here. I will draw out a very important diagram for you. Okay. Let me make it a little nicer. Okay, I will draw this. This is the component of weight along the slope. I'll call this W slope. Okay, in short, WS. Okay, in short, WS standing for the component of weight along the slope. And I want to draw a subsequent other component. This component is into the slope. In other words, it's normal to the slope. So this is W per. Right? In other words, perpendicular to the slope. Okay, so I can either write it as perpendicular like that, or I can write it as P. So I'll write it as WP instead. So the component of weight perpendicular to the slope. Now remember, I only care about the forces on this direction. So I hope you can see, if I try to resolve the weight here, well, I actually turn out, right, killing NCF and WP. Why? Because they are perpendicular to the slope. When you resolve something perpendicular to an axis, it becomes 0. So the next thing I need to do is find the relevant angles. So I want to extend this line out, and then it will be a lot clearer for you. So hold up. Okay. If I extend the weight now, like that, I hope all y'all can see that this angle here, right, this angle here is 90 minus theta. Okay, in case you're wondering, right, why is it 90 minus theta? You see, right, if I pluck out this and this, I get a nice triangle, right? So I get this triangle. This is W. This is this is 90. This is theta, right? So how much is this part here? This is 90 minus theta. Okay? So quite simple, quite simple. Then if I were to draw out the perpendicular portion, which is now WP, this will be theta. Okay, in case you're wondering, wait, why is it theta? Because this is 90 minus theta. right? Then isn't this 90? So you have 90 as the big right angle there. You minus off 90 minus theta, you get theta. So this here must be theta. Okay. So then from there, I will draw only the relevant components. Look, I'll draw W here. I'll draw W along the slope. I'll draw W perpendicular. This here is theta. To make it a bit more precise, it should be this length. Okay. So now I'm only resolving for the forces that I care about. You realize, remember what I said? I only care about the forces along the direction of the slope. So I'll write here on the left, the net force on the slope will just be WS. Okay, in case you're wondering why again, how come normal contact force is gone? Because if I were to draw normal contact force on the ball, right, this is the ball. I have to draw normal contact force. And I want to resolve along the slope, right? This angle is 90. So you go and take NCF, right? You try to resolve it to 90 degrees. You won't get anything. You will get 0, right? Because it's NCF cos 90. So you get 0. Okay, so that's why you realize the net force is just literally the component of weight parallel to the slope. Okay, and that's why I've written here W, which is weight, and just the component parallel to the slope. That's it. Okay, so what is this? This is going to be mass times gravitational field strength times sine theta. Okay, so for those of you who have been with me for a while, okay, I will draw my little cheat code that you guys know about. So look over. Once again, this is W. This here was W per. This is WS, right? And so this angle was theta. If you want to move opposite of the direction of theta, you're moving out of the angle. A very nifty trick is you just multiply by sine. If you're moving into the angle, you multiply by cosine. Okay? If not, you can always draw it out, right, as your right angle triangle. So if that's better for you, okay, I'll draw it out as a right angle triangle. Meaning this is WS, this was W per, and this here is W, right? And yeah, so quite standard. Then from there you can just use sine of theta. Okay, so wait, you know that sine of theta is going to give you, oh sorry, give me a sec. Okay. Sine of theta, you can identify the correct angle. So this will be 90 minus theta, and this will be theta. If you want to find sine of theta, it should be the opposite over the hypotenuse, which is WS over W. So from there, WS is W sine of theta. And so quite basic, quite standard. That's exactly how I got mg sine theta here. Okay, and now I haven't found the acceleration yet. So let me erase the working on the right. Okay. I need to go and find the acceleration now. The acceleration now, right, you find via Newton's second law. Okay, so I'll write here a little note on the right. By Newton's second law, we know that the resultant force on the object is the rate of change of momentum, which in other words is the rate of change of mass times velocity over time, right? And so we can also say that for a constant mass, it is mass times the final velocity minus the initial velocity over time. And then what's this fancy thing here? Isn't that just acceleration? Yes, right? V minus U over T. You learn this all the way in what? Sec 4, Sec 3 even, right? So this is MA. Then, so you can see I can just plug that in here because F net is resultant force. So MA equals to mg sine theta. What can I cancel out? Easy, just cancel M. Okay, and so you can say that finally I know that the ball will accelerate at g sine of theta. Okay, so definitely one of the harder questions, right? Because they never give you any values. You must just work everything in terms of the quantities listed as g and theta. Okay, but I hope to have conveyed the logic here, you should be writing things out. You should be drawing out the force, the free body diagram, so you can find the answer clearly lah. Okay, so this was a more challenging question. Okay, hope that was clear for you all, and just practice a bit more lah. So slope questions are likely to come out for the end of J1. That's what I've seen in a lot of promo papers. Okay, head over to example B. Now this one, right, if I were you, right, I'll draw like 5 stars. I'll draw a lot of different things on this worksheet just to make sure you know this, because it's very, very common. This question is so common for promos. Like, I can close my eyes, right, and know that probably half of you guys who will see this in promos, okay, if you are in J1. And for A levels, maybe not lah. A levels, you know, like they like to test you a lot of other crazy topics. Okay, but if you're in J1, I'm quite sure this will come up. Okay, but don't spot. Physics is not a topic where you can spot. Study everything. Okay, this is just one of those more common ones. Okay, so let's read the question first. A tennis ball approaches a tennis racket of a man horizontally. So there's this guy, right, playing tennis. He's about to swing his bat and hit a ball. Okay, the ball was originally coming to him horizontally. So the ball has a mass of 100 grams and it's approaching the racket at a speed of 5 meters per second. The man, right, swings the racket, okay, and then he hits the ball. The ball now leaves with the same speed, 5, but this time around with a 30-degree angle from the horizontal. And then they tell you the collision is 0.1. Now they ask you to find the change in momentum, okay, and they ask you to indicate the direction of change in momentum clearly. So, right, look, so many of the students, right, are so tempted to just write, oh, the change in momentum is 0 because the final speed, initial speed is 5. So since momentum is mass times velocity, the velocity is 5, therefore there's no change. Wrong. Remember, velocity here cares about direction. Okay, I repeat, velocity cares about direction. So even though they have the same speed, 5 and 5, they have different velocities, and therefore they have different momentum. Because momentum here is a vector, so you cannot just use scalar addition to find the answer. Okay, so everyone draw this with me. You have the ball here. Okay, the ball here of 0.1 kg, right? It's moving with this speed, 5.0 meters per second. Okay, we'll call this U1. Now, you know that after it gets hit by the racket, okay, so you can imagine the racket just completely hit it this way. It's moving off now with a final speed 30 degrees from the horizontal of 5 meters per second. Now, I hope it's clear, right, that actually you have different momenta here. Momentum 1 was horizontal to the left. Momentum 2 was at an angle to the right. So actually, I can straight away, right, find the change in momentum by doing vector addition. So the change in momentum, the change in a value is just its final value, take away its initial value. Right? So look, which is the final momentum here? It's this guy. Which is the initial momentum? It's this guy. So this is rho F, rho I. Now, if you want to find rho F and rho I, you can subtract vectors, right, by doing this. You add the negative of the initial momentum. Okay, so look over, remember, right? This is initial momentum. If you want to find the negative of initial momentum, right, intuitively, it's just in the opposite direction. Okay, so meaning to say, look, this is minus rho I log. It's just 5 meters per second in the opposite direction. That's the negative of the initial momentum. So, to make it a little clearer, I want you all to sketch it out like that. You draw out your initial momentum first. Your initial momentum was like this. Okay? And you know that this is 5 kg, or rather 0.1 kg times 5 meters per second. So we can say it's 0.5 kg meters per second. And this is final momentum. Now you want to add this other momentum here, which is the negative of initial momentum, which looks like that. Right, that's what I've drawn. I'm copying this here. Okay, so this is why I'm adding two together. And how do you add vectors? You have learned this all the way back in Sec 4 and in well, the start of kinematics also, right? You have to add vectors. Some of y'all learn it in measurements, right? They do, a lot of schools actually put in the vector addition here. Now let's draw the following diagram. This is final momentum. This is negative of initial momentum. And the change in momentum, okay, wait, let me aim. Give me a sec. Okay, the change in momentum is this. Right? You're adding rho F to negative of rho I. This is the change in momentum. So quick question, what is this angle here? What's alpha here? Alpha here you can obtain by considering that this was, okay, give me a sec, that this was 30 degrees. Right? You know that the final momentum is 30 degrees from the horizontal, and the negative of initial momentum was also horizontal, right? Because momentum initially was horizontal, so the negative of momentum initially is also horizontal. So if this angle, this fella here is 30 degrees, how much is this angle? You know that these are two parallel lines, so interior angles here, this is 150 degrees. And so this is basic sec 4 math, I think. Okay, and so yeah, so you should be able to find this now. I'll label very clearly that this is 0.5, this is also 0.5. You want to now find out the change in momentum. How do you do that? You have to use cosine rule. Okay, and so cosine rule goes this way. C square is A square plus B square minus 2AB cosine C. Okay, so you plug this formula in, and you can tell that, well, if you want to find the change in momentum, it's 0.5 square plus 0.5 square minus 2, 0.5, 0.5 cosine of 150 degrees. And you square root the whole thing. Because you don't want C square, you want C, okay, which is the change in momentum. So you plug this in, right? Okay, give me a sec, I pull out my calculator. And then you can get the change in momentum. Okay. So okay, I get 0.9659. Yeah, I get 0.9659 as my value. Okay, and this will be kg meters per second. Now, a lot of the students, right, like so the mid-tier ones are those who are like getting C's and B's, right, for your promos. Okay, this is not where you stop. Okay, this is not where you stop. Why do you not stop here? Because momentum is a vector, meaning you have to account for the direction also. Okay, I repeat, you have to account for the direction. You got the magnitude already. You get here, you celebrate, you're not done. Okay, please remember, you're not done. You need to find the direction here. Okay, so let me call this angle alpha degrees. Okay, this is an isosceles triangle. I hope you know that already, right? Because both the sides are equal. So if the angle here is 150 degrees, then I hope you agree with me, both of the angles on the side should be 15 degrees, right? So remember, every time you talk about a vector, you should always account for the magnitude and the direction. So I'm going to finally refine this, and I'm going to take into consideration the significant figures that they've given to me. The lowest significant figures in this question, clearly 2SF. So all I give is 2SF as my answer. 0.97 kg meter per second, and the angle is 15 degrees, will be clockwise from final momentum. Okay, and so that is the answer for part 1. Okay, listen, it's probably coming up. Okay, if I were you, I will take a screenshot of this. I will make sure I know how to do this kind of question. Okay, that's part 1 done. Part 2 is easy. Okay, so let me erase some of the working on the side, so I got some space to write. Okay, part 2 will just be calculating the force. So look, the net force by Newton's second law is just the rate of change of momentum. So the average net force will be change in momentum over change in time. And the change in momentum is 0.97. Okay, wait, I'll use 4 significant figures first. And then divide by the time. So the time here is 0.5 cosine, 0.1. And then once you get this, you should get 9.659 newtons and 9.7 newtons. Okay, and remember, right, by our Newton's second law, we know that the net force acts in the same direction as the change in momentum. So we can also say that it's 9.7 newtons, 15 degrees clockwise from final momentum. Okay, or you can also say 15 degrees clockwise, or rather you can also say like the final thing that you can say in the same direction as the change in momentum. Okay, that's it. That's practice example B. So quite standard. Okay, I got a question from some of you guys. Will I get marked down for rounding it up to 3SF instead of 2SF? Yes, your overall paper, right? If your schools are very strict, which usually they are, they will want to get the exact, the proper significant figures for each part. So overall, right, your whole paper they will -1 for each paper lah. So paper 2, paper 3. This doesn't apply for practical. Practical, right? They can minus a lot of marks. So if it's paper 2, paper 3, or your promos, right? Then you would know that okay, they'll just -1 or 2, yeah, from your whole script. And then can I say 15 degrees with respect to horizontal? Can, Clara, you can say that. Another one. How come cannot use 5 cosine 30 as V and MV minus MU to find change in momentum? 5. 5 is off, right? Because it should be 0.5. And Crystal, if you actually use and resolve the forces in that way, that is valid also. Is there any rule on Sfdp to round up for structured papers? Yes, yes. So for the questions here, right, you're usually going to give to the lowest degree of what the question has given to you. So if you look over at the data given, right, there's 5, there's 100, there's 0.10 and 30. Now all of them, right, are 2SF except for this fella here. So 100 grams could be 3SF, right? Could be 3SF. But you always want to use the least significant, rather the least degree of accuracy. So in this case, the least degree of accuracy is 2 significant figures. So that's why you take 2 long. Okay. Okay. Okay, Crystal, later you can send me your working, then I can just take a look at it and let you know why that's not right. Okay, if not, I'll move on to question C. This one's easy. Yeah, I love this one. This one's giveaway, honestly. So an object of mass 4.5 with an initial speed of 1 is acted upon by a force with the following time. Okay, if the force acts in the same direction as initial velocity of the object, what is the velocity at t equals to 9 seconds? So here, remember, the impulse. Okay, wait, my stylus is a bit crazy. Okay, the impulse is also the area under the force time graph. Okay, so it's the integral of resultant force with respect to time. In other words, it's the area under ft graph. So this impulse is also the change in momentum. So you know that the change in momentum, right, is just this area. So you can find the area. So it's half times 7.5 seconds times 5. Yeah, here. I'm finding this area. Now, some of you guys might say, then what about this section here? Right, so there is no further force, right, from 7.5 to 9. So that's why I don't use the timing 9, it's just 7.5. I'm finding an area of the triangle. Okay, that's it. Okay, and wait, let me take my calculator. Okay, you should get 1.875 kg meter per second. Okay, so very important now. Think about it this way. You had an object 4.5 kg. Your initial speed is 1. Meaning I had initial momentum already. My initial momentum is 4.5. Right? Because it's just 4.5 times 1. Okay. Now, if I have the impulse, right, in the same direction, then I hope you all agree I just need to add up this change in momentum. Yeah, I just need to add up this change in momentum and I'm done. Okay. Give me a sec. This was 18. So hold up. Okay, that's it. Yeah, and finally, the final momentum is just the initial momentum plus the change in momentum. Okay, so initial momentum, we've already covered it. It's here, 4.5. Final, the change in momentum is 18.75. So you add those two together, you will get 23.25 kg meter per second. So finally, look, they're not asking for final momentum. They're looking for final velocity. at 9 seconds. So lastly, last step is final momentum is m times v, right? So if you want to get v, it is final momentum over the mass. So 23.25, you divide by the mass of 4.5. Easy. Okay, and what do you get as your final answer? You get 5.16. Okay, as your final value. So it's 5.2 meters per second in the same direction. So yeah, that's the idea. So I hope that was clear. This was easy. Usually this kind of questions would come out as like a way to sort of save you from promos. Okay, I got a question here. Do we have to round up to smallest SF for exact numbers? Yes, you still have to. So you want always 2SF or 3SF in the case of your questions. You use the least significant figures. In this case, it's 2 lah. Okay, so you always should change. What if the graph doesn't show Fnet? So yes, if the graph doesn't show Fnet, then you must be careful. If there are any other forces acting on it, then you perhaps need to subtract to get Fnet. But in this case, for this question, right, they show only this single force acting on it. So then, therefore, you should only look at this. Yeah. Okay, and subtract. Okay, for questions, if let's say it's more complicated, so there are more than one forces, right? There's more than one force, sorry. You have to account for it, right? And eventually get resultant force. So notice my statement here, right? I say that impulse is the area under the resultant force time graph. That's why I write RF dt. So if, say for instance, this force graph, right, is only one of the forces acting on the object. And let's say the question becomes more complicated. There are more forces. Then you have to account and make sure that you find the resultant force on the object at all times. That's it. Okay, but it won't be present in this question now. How do you find momentum from 7.5 to 9? So look at this graph. There is no more force acting from this region. Right? So in other words, there is no further change in momentum from 7.5 to 9 seconds. Yeah, that's the logic here. Okay, so that's why I could ignore from 7.5 to 9. Okay, now wait, I want to move on to the harder questions. This was a fun one. I felt that this was very beautiful. So look over at practice example D. The figure below shows the variation of net force that body A exerts on body B in a collision between two bodies. Okay, in the figure above, sketch the force time graph on B that B exerts on A. So remember, right, by Newton's third law, the force of A on B is the negative of the force of B on A, right? Equal magnitude, opposite direction. So actually, it's just a mirror image lah. Okay, that's it. So that's the answer for part 1. So done. Okay, force is a vector, so that's why I have to put the negative, and I have to draw it as a negative value also. Okay, that's the key idea. Then let's look over at part 2. Write down your explanation for your answer in part 1. So the explanation should be quite standard. Okay, you always be using Newton's third law in this kind of question, right? Because it's one colliding with another object. So you must say, right? Okay, here. The force that A exerts on B is equal in magnitude but opposite in direction to the force that B exerts on A, in accordance with Newton's third law. Okay, thus the force of B on A is always equal in magnitude but opposite in direction and therefore negative. Okay, to the force of A on B as shown in the figure above. Okay, quite standard. This one is just Newton's third law. Okay, look over at the part 3. Explain how your answer in 1 and 2 is consistent with the principle of conservation of momentum. Okay, this was my favorite, right? Because it really tests whether or not you understand what's going on. So look over here. Look over here. I'm labeling, right, the first guy as A. What's the change in momentum of A? The change in momentum of A is the impulse, which is this area. How about the change in momentum of B? It's also this area, which is the area of the force time graph under B. Both of them have the exact same shapes by an opposite direction. Meaning the impulse of A, right, is exactly equal in magnitude, but opposite in direction to B. Okay, so we'll write out the last statement. This was my favorite question. Okay, come. So look, we know consider momentum of A and B. We write here that the change in momentum of A is the area under the force time graph of A. And the change in momentum of B is the area under the FT graph of B, which is also equal to the impulse of A and the impulse of B. Okay, so let me add on. I will then go and say that as stated in 1, wait, 2, I think 2 was the question, right? Where they were equal magnitude, opposite direction. The force of A on B is equal in magnitude, but opposite in direction to the force of B on A. Hence, the impulse on A is equal in magnitude, but opposite in direction to the impulse on B. Okay? So, considering the total change in momentum of the system of A and B, total change in momentum. Okay, I'll write out the last statement in my handwriting. No space. Change in momentum of system equals to change in momentum of A plus change in momentum of B equals to 0. I hope it's clear it's 0 because both of them have the same magnitude but in the opposite direction. Right? So you can see the change in momentum, right? When you add up both of them, they cancel out to become 0. Okay, finally, last statement. We link back to the principle of conservation of momentum. Thus, there is no change in total momentum of the isolated system, and hence the principle of conservation of momentum is consistent with 1 and 2. Okay, so that's pretty much it. Right, quite standard. I think this was a fun question. Okay. So I got a question. Do we need to state the same type of force, etc.? Not necessary. For this question, they are more focused on whether or not the overall momentum is the same in terms of the magnitude and the direction. But if you do include it, then that will be good. So you can also say that the force exerted on A and B are the same nature. So that's fine. Okay, so I got a question for part C previously. Okay, for those of you who want, you can take a screenshot of this now. Okay, and then I will move over. Okay. For the second one, come, nice here. right, for part C. So I got a question, how come you can just add initial and final momentum? Aren't they vectors? Yes, they are vectors, but look, they are in the same direction, right? So if they are in the same direction, so imagine now this is initial momentum, and then the change in momentum is like that. Do you agree that, oh, it's just addition really? You can just add it as if it was a scalar because they are the same direction. And so that's why I can just blast together lah. Okay, and then our shank. You can see already, right? Shank. Okay, then yeah, that's it. Can I move on? The harder question now. Okay, and listen, hey, wow. The next one, right? I'm like so confident it's coming out for your promos or your A levels, or for those of you who are in J2, right? Your prelims. I'm quite confident this will come out. If they are testing collisions, I'm like quite certain it's coming out. For the J1s, right? Like it's like almost guaranteed to come out lah. Okay, don't quote me on this, but I'm very sure it's coming out. This was a little paper I gave to my J2s just last week. RJ 2020 prelims. I adapted the question a little bit. I removed one part of it because that part wasn't relevant to this question or this topic anymore. So just briefly read this. Body A of mass m and speed u1 makes an elastic head-on collision with body B of mass 2m and speed u2 shown in the figure below. Okay, so describe the subsequent motion of the two bodies knowing that it is head-on. So remember, right, just now I went through about what head-on means. When we say that there's a head-on collision, it means that the two momenta at the start were traveling along the same line. So remember, right, momentum is a vector. And based on the principle of conservation of momentum, there should be no final change in momentum. So when they collide head-on, right, the total momentum of the system remains constant, and it should still be along the same axis. Meaning, once they separate, they still travel along the same lines. Okay, so that's what head-on means. So you can say, right, balls A and B will move with momentum that is along the same line. Okay, so some schools, right, they actually like to write something along the lines of the initial and final momenta of A and B are collinear. So I think you all know what this means from Sec 4, E-Math, Sec 3, I don't know, can't remember when you all learned the word collinear, but it just means along the same line. Okay, some of the other schools will also write something along the lines of the centers of mass and gravity, okay, on A and B lie along the same line throughout, or rather before and after the collision. Okay, yeah. So that's what it means when we say a head-on collision. Okay, so I know some of y'all realize it's 9 p.m. already. If you need to leave, by all means. Okay, if not, I'll move over to elastic collision. So elastic collision, what is an elastic collision? Don't worry, later, right, I'll send this file to the chat. So for those of y'all who haven't copied down in time, no stress. Right? I'll send this to the chat later. Okay. So the collision is elastic. What does an elastic collision mean? Basic, here, an elastic collision is one where the total kinetic energy of the system is conserved and the relative speed of approach of A and B is equal to the final relative speed of separation. That's it. Okay, so that is what elastic collision means. So RSA equals to RSS. That's the key idea. Okay. Now, let's quickly go to B. So listen, for part B, right, this is very likely to come out. And the strategy is this. You come out with two equations first. One equation is by considering the principle of conservation of momentum. The other equation you come up with via the elastic considerations, which means the relative speed of separation is the relative speed of approach. Right? So you have to use these two methods. So I say, very quickly, jot down, right, your two equations. First one will be stating the direction, which one you're going to take as positive. So taking rightwards as positive. Then by the principle of conservation of momentum. Okay? Okay, some will also write it as COM, by conservation of momentum. Okay, then what we can say is initial momentum is equal to final momentum. So M1U1 plus M2U2, right? Because that's the total initial momenta. It should be equal to M1V1 plus M2V2. Okay, so then from there, right, you just plug in the values. Okay, and in this case, M1 will be M times 2. Oh, sorry, 4. And then M2 will be 2M times minus 2. Why minus 2? Because it's traveling to the left, so it's negative. Okay, and then this will be equal to M1 V1, which is MV1, plus M2 V2. Okay, so M2 is 2M V2. Okay, and this is all conservation of momentum so far. So let me drag this to the left. Not later I run out of space. Okay. And then finally, you'll realize that on the left hand side, it all cancels out, right? Because 4M plus minus 4M. So this becomes 0. And this is MV1 plus 2MV2. That's it. Okay, and you can cross out the M. You divide by M on both sides. And one of the equations that you get at the start, right, from here is V1 equals to minus 2V2. I'm just bringing the 2V2 to the left. That's it. Okay, and then now we do our second equation. Okay, anyway, this is equation number 1 first. Now, considering elastic collision, by the principle of conservation of energy, I know that relative speed of approach is relative speed of separation. So from there, right, you will straight away use the relative speed of approach, which is U1 minus U2 equals to V2 minus V1. Okay, so this one you must be careful. Notice that once again, velocity here is it's a vector. So when you put the minus U2, right, you must remember, right, that U2 is already negative. So therefore, the answer should look something like this. 4 minus 2 equals to V2 minus V1. So 6 equals to V2 minus V1. Yeah, key idea. Okay, and this is our second equation, which is number 2. Finally, you just sub in and solve. So you sub 1 into 2. Okay, so you'll get 6 equals to V2 minus V1, which is minus 2V2. Right, that's it. How do I get this? You just plug in from here. Right, that's it. Then once you click in, right, you should get 3V2. And then this is 6. So then how much is V2? V2 is 6 over 3, which is 2.0 meters per second. And V2 was B, right? We're talking about V2 as object B. So my answer for B is 2.0 meters per second. Okay, so this is one of my answers. Let me box it up so it doesn't get confusing. Okay, now if I want to find velocity of A, I'm trying to find V1. So look, V1 is minus 2V2. That's from here. That's from here. Okay, then I know V2 already. V2 is 2. So I'll straight away put minus 2 times 2, which is now minus 4. So that's minus 4. Okay, so yeah, done. Quite standard. These are the kind of questions that you must be well prepared for. It's a very easy question. It's considered easy, by the way, even though it's a RJ question. It's considered doable, very easy. You have to be prepared for these kind of questions in your promos and in your A-levels. So this is about A-level standard. Yeah, this is definitely about A-level standard. So yeah, make sure you get this right. Okay, if not, for those of you who haven't copied down in time, no worries, like I mentioned. We'll finish off F first and then we'll conclude today's class. I want to go through F first, so that's why I don't want to waste your time. I'll send this to the chat later. Okay, look over at F. The figure below illustrates two spheres of masses M1 and M2 moving along the same straight line with initial velocity u1 and u2. After collision, they stick together during the impact. Okay, and then they move off with common velocity v. Okay, come on, I see this one's quite an interesting thing. You have to straight away see this part, stick together. When two objects stick together, they have the same velocity as they leave. So straight away, right, you should write out that the relative speed of separation is 0. They don't separate, they are sticking together. That's why there's no relative speed of separation. On the other hand, right, they had different initial velocities. So that means the RSA should be u1 minus u2, which is non-zero. So if the relative speed of approach, right, is non-zero, but then the relative speed of separation is 0, is this elastic or not? The answer is no, right? Remember, for all elastic collisions, relative speed of approach is relative speed of separation. Now, we've proven here, right, based on this logic, that it is not elastic. That's it. Okay, so it is inelastic. The RSA, relative speed of approach, okay, is u1 minus u2, which is non-zero. Whereas the relative speed of separation is 0. Thus, the collision is not elastic. That's it. I think quite easy lah, right? Quite doable. Okay. Yeah, that's how you should answer E. Now, they want you to state in terms of M1, M2, U1, U2, and V to represent the change in momentum of, firstly, the sphere of mass 1 and the sphere of mass 2. So first one, for mass 1. Change in momentum is final momentum minus initial momentum, which is just M1V minus M1U1. So it's just M1 V minus U1. Okay, next one for mass 2. Change in momentum is just rho final minus rho initial. And it's M2 V minus M2 U2. So it's just M2 V minus U2. Done. So I got a question. Can we, for part A, right, can we just say that since they stick together, that's why it's inelastic? Cannot. It's not precise enough. You need to explain exactly why it's not elastic. So this will be the way. And yeah, so you have to state it, I have to point it out very clearly. Okay. Yeah, then finally, let's move on. Part C. Using answers to B, state an equation to represent the conservation of linear momentum of the collision. Okay, so here, let's see. Look, initial momentum equals to final momentum by conservation of momentum. So this means that the change in momentum is 0. Then you can say, therefore, okay, wait up. You'll just write change in momentum of 1 plus change in momentum of 2 should add up to 0. Okay, right, that's the change in momentum, which means M1 V minus U1 plus M2 V minus U2 is 0. Okay, and yeah, that's pretty much it lah. So when you find the two change in momenta, you add it up together, then that's the overall change in momentum, that's 0. Vishvesh, not necessary. If you do cover relative speed of approach and separation, that will give you the mark. For part D, explain the energy conversions that result due to the collision. So you must know that in this case, this is considered inelastic. So KE is not conserved. So then you are expected to know in your syllabus that the kinetic energy was converted into other forms. Now, in case you're wondering, what other forms are we usually having when we have inelastic collisions? Thermal, which is your heat, and then sound. So that's pretty much it. So the answer for this will be, given that the collision is inelastic, kinetic energy is not conserved for the system. Hence, some kinetic energy must or was converted into other forms such as heat and sound energy. Okay, and in particular heat, right? The better way to write it is thermal, and then sounds okay. That's it. Okay, done. So that's pretty much the result of the collision. So I got another question. Can I write M1 U1 plus M2 U2 is M1 plus M2 V for part C? Yes, can. That's valid. So if you do write that, it's the same. This is the same thing. Right? They're equivalent to one another. On the left hand side, I have total initial momentum. On the right hand side, I have total final momentum. Yeah, that's it. Perfect. No, that's accepted. No problem. Okay, last one, easiest. Here we are finally finding the final velocities. So I'll just plug in this formula also. So M1 U1 plus M2 U2 is M1 plus M2 V. Okay, and then you just start in the numbers lah. So M1 is 1, initial U1 is 1, M2 is 2, initial U2 is 2. Then you have 1 plus 2 times V. Okay, if you want to find the final velocity of the balls, the spheres, is 1 plus 4 equals to 3V. So 5 over 3 equals to V, and you can say that V is 1.6666 blah 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 blah. So 1.7. That's it. For Vikram, generally, right, after the conversion to elastic potential energy or something else, you must still go and say that for an inelastic collision, it's then converted into heat and sound. Okay? So yeah, that's the key point here. Okay, how does the explanation describe the subsequent motion of the bodies? Wait, give me a sec. Are you talking about this one? Okay. Yeah, okay. So Samantha, because the relative speed of the approach and the relative speed of separation is talking about the subsequent motion already. So that's how it answers the question. For E, I don't have to take into account the sign convention. Yeah, you do have to take that into account, Riku. But you realize that U1 and U2 are already these two are velocity. Correct? Yeah. So if they are velocities ready, right, and they are already given to you as both positive, then in this case, yeah, straight away you can just plug in the numbers. That's the logic. Okay. Okay, so far okay. Are you all good with this? If not, yeah, that's pretty much the whole questions, the whole 5 questions and the objective for today. I'll send this in the chat. Then that's pretty much it. I think you all should also check out the group chat, because I believe like throughout this week there will be chem crash courses for certain promo topics. There's also math. There's basically everything all your H2 subjects, except for bio, I believe. Like there will be a free crash course one of these days. So for my current students at AMA, I'll send the link. You can go and join the chat. For the rest of y'all, yeah, do participate. Go and recap some of the topics. There will be more details given about the notes that Daryl and the team are coming up with. So if you want to get our notes, we'll put a link out there. And then there's a crash course also, like official one in October. by then you would have been done with your promos. Okay, so if you didn't fare as well as you would have liked to, the crash course will be, I think it's covering 4 different modules. So you're invited to come for those that you have already covered in J1. It's actually meant for the J2s, but we'll be breaking it down into module specific like crash courses. So module specific meaning you'll cover like certain things in Newton mechanics altogether, and then like another module will be like for different category. So here in J1 we'll cover mainly module 1 and module 2. So if you're interested, you can come. For the AM Academy students, you've covered everything already. Okay, but if you still want to come for more, yeah, do text me and then I'll let you all know about this. That this recording will be uploaded onto the YouTube channel lah. So Daryl is in charge of this. He will settle it. Okay, and it will be on YouTube. So y'all can go and check it out. Then, if not, yeah, hope this was okay. Okay, let's see. So some of you guys still have some questions. For example B, why don't I get the same answer when I do this? 0.15 cosine 30 plus 0.1 times 5. Cheyenne, you are not adding up vectors in the correct way. So you see, right, when you do 0.1 times 5 cosine 30 and 0.1 times 0.5, you are finding them in one direction, but you are not resolving, right, in like all directions. So in other words, if you're ever adding up vectors, you have to consider it as your tip to tail diagram. Okay, so let me explain. I'll add you one page here. So one of your attempts here was to just write. Sorry, let me copy down what you wrote. 0.1 times 5 cosine 30 plus minus 0.1 times 0.5. Yeah. Yeah. Okay, cool. Yes. Times 5, right? Yes. So this is still not correct. Okay, let me explain why. What you're trying to do is for the 5 cosine 30, right? You are finding the 0.1 times 5 cosine 30. You're finding this, right? The final initial momentum, right? So this is final. And then you thought that you are resolving here, correct? Right? So you're resolving it through this 30-degree angle. And here the problem, right, Cheyenne, is that when you are doing this, okay, you are only finding the horizontal component of final momentum. You're not accounting for the vertical component, which is here. Right? This is rho F vert, this is rho F horizontal. So when you do the cosine 30, right, you're only counting for horizontal final momentum. So that's why you can't do this. You have to also bear in mind, right, of the final horizontal, final vertical momentum. So if you wanted a more precise one, right, you would do horizontal. You go and find the total final change in momentum, and then find the vertical change in momentum. And then after that, you go and plus these two together, right, using your Pythagoras theorem. And then that's it really. So meaning to say, if let's say I was resolving this again, the horizontal momentum, right, remember is rho F minus rho I, right? So rho F is, it looks like that. This is 0.5. This was 30 degrees. Okay, and when you add up the two of them, right, the vector diagram looks like this. If you decompose both of them, this is 0.5 cos 30, and then this here is 0.5 sine 30. So if you want to add up the horizontal, you are right for the horizontal section. So change in momentum horizontally is 0.5 cos 30 plus 0.5. Okay, then vertically, right, you still need to add this, which is 0.5 sine 30. Okay, so Cheyenne, you are doing it only horizontally. You must now also do it vertically, and then finally, right, you have to go and do the overall change in momentum, which is both components, the horizontal like that, 0.5 cos 30 plus 0.5. And then, oh, sorry, this one is vertical. Give me a sec. You're adding this now. 0.5 sine 30. That's the vertical change in momentum. Then this was 0.5 cos 30 plus 0.5. So then this, right, if you add up the two of them, then you end up getting the overall change in momentum. So if you do this, then you go and press in the calculator, right? The value of this will be by Pythagoras theorem. You should get 0.5 cos 30 degrees plus 0.5 square plus 0.5 sine 30 degrees, whole thing square. So let me just check and evaluate, because this method should also work. Yeah, exactly. So you should get the same thing, 9659 blah blah blah, which is 0.97. Right? So yeah, so that works. So remember, right, if you want to decompose and add, then you must do both horizontal summation and vertical summation. It cannot just be one. Bye, Ryan. Thanks for coming. All the best for the promos. Let's do it. Okay, then any other question? Okay, wait. I got a question from Summer. Why practice B cannot just set a sign convention? Let's see, practice B. Yeah, you can't, because you see sign convention, right, is taking into consideration motion in one line, correct? For example, if I use sign convention, it means that right is positive and then left is negative, correct? Then what happens if now I have at an angle of 30 degrees? You see what I mean? You don't actually manage to get into account, right? Like the 30-degree a different angle. You have to either have it on the same line for positive and negative. So that's why it's not doable. You should be using them as vectors like that instead. That's the logic. Okay, yes, best is always to draw triangle. Best is definitely to draw triangle. When you're drawing your vector addition diagrams, right, you realize that you add up as a vector in this way, in the way that I solve here. This is the safest. It's always the safest. Because you consider the direction as well as the magnitude. Then you have to either use cosine or sine rule to solve, and that's it. Yes, Crystal, you must consider 5 sine 30, which is what I've done here. Yeah. Okay. So I'll send this to the chat, and then yeah, if you all have questions, you can PM me on that, and that's pretty much it. Okay. I got a question from Reese. During collision, K converts to EPE. Does EP convert to thermal and sound energy, or does EPE remain? So it depends, Reese. If you're still here, if let's say you have an elastic overall collision, the EPE must be converted back into KE. Yeah, that's the key idea. If it is inelastic, then the EPE could have been converted into thermal and sound. It will be converted into thermal and sound. Okay, so you have to overall care about whether the whole collision is elastic or inelastic as a whole. Summer is also asking, can I explain what are the two equations you have to come up with for the tension in the rope question? For the tension in the rope question, right, it's not two equations. It's just, okay, wait, let me get back to that. Here. Yeah, so for rope, there are two things that you must know. So it could be two equations, it could be more than two equations, it could just be one. But the idea is the magnitude of acceleration for both objects on either end of the rope are the same. Then the tension is the same in magnitude. Yeah, that's it. Okay, and Reese is asking, even if it sticks together, EP is converted into thermal and sound energy. Yeah, correct. Because you see, right, Reese, the two balls will not be compressed forever. So then the EP eventually, right, as over time, right, the EP reduces to 0 when it is allowed to go back to its original shape. Yeah. Okay, and yeah, that's pretty much it. Okay. So give me a sec. Okay, let me see whether there was a question here. No. Okay, then that's pretty much it. Yeah, if not, we're done for today. I'll send this on the chat now. See you guys. Thanks for coming. Do go and check out our other revision slots as well. Okay, see you guys. Goodbye. No problem.